right, the first unit we're talking about Earth's interior. So with Earth's interior, we'll be learning about the layers. The first lesson is about Earth's core. We're going to relate the movement of seismic waves to the composition of the Earth's core, and we're going to describe the characteristics of the inner core and the outer core. Those are the two main things you're doing for this unit. Okay, or for this lesson. Okay, earthquakes and seismic waves. Why do we use those? Because our normal instruments cannot get into the center of the Earth to learn about them. So the waves produced by an earthquake, we can record the data from those in order to learn about the center of the Earth. Earthquakes are produced when Earth's uppermost layer moves suddenly. Those shakes and trembles can pass through the Earth, and they can also cause massive destruction. Seismic waves are the shock waves produced by the earthquakes that travel through the Earth. Shock waves are waves of energy. It's important to know that. The energy has to transfer somehow, and they're going to go away from the source. There are two types of waves, P and S. If you do research, you can learn about another type of wave. We are going to focus primarily on the P and S waves. But if you ever come across a third wave, there is a third wave. We just won't be talking about that one. Seismographs are the machines that will record the P and S waves. This is one style. Guarantee that there are more modern styles than this one right here. And there are ways that you can use your computer to help sense seismic waves. Seismic waves penetrate through the depths of the Earth and return to the surface. So they can actually go through the entire Earth and they can be sensed on the other side. And we'll go into more detail on that. P waves are the primary waves. They're the first ones generated, and they move horizontally. So they're going to move back and forth. Horizontally, like in the same plane. S waves are secondary waves, and they're the second ones that come. These are the ones that are more damaging because first of all, they move slower, and they move vertically. So they would be moving up and down as they're going forward. So there's more movement with that. And if you notice up here, the S waves are going to cause more disruption on the seismograph. So here's the P waves. P waves just show that there's some activity, which we wouldn't even be able to sense those. And then when the seismic waves come, those are the ones that we can sense. If you look here, if there's an earthquake at the North Pole, those waves are going to end up arriving here and here. It changes with the core. So you'll notice these red lines. These red lines are attempting to go, our P waves are attempting to go through, but notice the S waves cannot. The S waves, once they get so far, they can't go into our core. Okay? But they can both arrive if they're traveling along the surface to other areas that don't require them to go through the core. We do get a shadow zone where there's not going to be any of the S waves. And then on the other side of the Earth, we're going to get only our P waves. The P waves can travel through the center of the Earth because we've got different substances. It impacts the travel. Okay, so how do we identify the Earth's layers? Exactly that. So the difference in the wave actions at 2,900 kilometers below the surface suggests that there's a liquid layer. So that's going to be right here. We've got our liquid layer. And because of that, our P waves actually slow down and our S waves disappear. The S waves cannot travel through this liquid layer. At approximately 5,150 kilometers, the P waves increase, so that's our solid layer. So because there's that change in velocity between the inner and outer core, we know they have to be made of different substances. So we know there's different characteristics for those layers. All right, the Earth's core. Why is it so hot? Hopefully you know that the center of the Earth is very hot. We can't travel into the center of the Earth because it definitely gets way too hot. It would end up melting anything we take down there. So there's three main sources of core heat. When the planet formed, it was extremely hot, and that heat is still kind of trapped inside of the planet. And it's been retained for a long time. It can't cool. Our crust on the outside of the Earth is keeping that heat in, and it can be up to 18,000 degrees Fahrenheit. Frictional heating can happen by dense material sinking. So as it's sinking, there's going to be some rubbing between the two materials, which is going to cause some heating too. And that can get up to 3,000 degrees Fahrenheit. So think about rubbing your hands together. That's friction, and that's some of that heating that's going on. and it's due to iron-rich material. We also have the decay of radioactive elements. There is some uncertainty on the abundance of the radioactive elements, but when those radioactive elements are reacting, it can cause heat. But there's not a ton of information on that. That's just something that we know could be happening in the center of, or like down in the core. The mantle traps the heat within the earth, as does the crust. It's going to prevent it from escaping. So measuring the temperature, we can't take samples, we can't send anything down to the center of the earth. It's just too deep. We can't physically get there. We haven't even gotten through the entire crust. But we can, since we believe that the waves tell us that there's iron, we can study the melting of iron at ultra high pressures. We can use lasers and high pressure devices to mimic the temperatures and pressures in the Earth's core. So the more that things layer up, the more pressure there is, kind of like if you dive underwater and go to the deep part of the water, your ears are uncomfortable because of the pressure, okay? And due to the uncertainties within all of this information, if you look at a different textbook or a different web source, you might see different ranges of kilometers. You might see different ranges of temperatures. There's no exact answer. We can give approximate answers, but because of the uncertainties of all our measurements, because we can't have them exact, we will have ranges. So I'm going to have you focus on using the data from the presentation that I have here. But just know, if you look at another source, you might very well see different numbers. And some of them will measure in miles instead of kilometers, so that will cause some differences too. Okay, so the inner core. The inner core we have determined is solid. It's our innermost layer of the earth, and it's made of nickel and iron. And the reason we think that is because of those tests that we've done, because of the speed of those the P waves traveling through them. The temperature is 5,000 degrees. We determined that nickel and iron normally melt at 5,000. The pressure, because there's extremely high pressure, because here in the center of the earth, all the rest of the earth, this entire layer is pushing on that. So because of that, we have extremely high pressures. People would not be able to even travel into the depths of the earth unless they had like an astronaut suit on because of the pressure change. So we do know that the inner core begins at a depth of approximately 5150 below the Earth's surface. That should say below the Earth's crust. If we want to include the crust, so the reason I have different numbers here is because if we include the crust can range from 8 to 32 kilometers. So these numbers here, the range, is allowing for that difference in heights of the crust, because if we have ocean crust, it's going to be thinner. If we have continental crust, we have a lot of land above the earth. So if we just think of it as below Earth's crust, we can focus on just one number. And we do know that approximately 5150 kilometers below Earth's surface, we have a difference in how those P waves travel. Nickel and iron, another reason we can determine that is because it explains the existence of the magnetic fields. Those magnetic fields, if you take astronomy, you should learn about how those magnetic fields help us. We'll talk briefly about them this semester, but probably not in a lot of depth. So just to stress again, the inner core is solid because there is a ton of pressure, which is then forcing the particles together and causing them to remain solid. When you get into the outer core, which we're going to talk about next, there's less pressure, which then allows the particles to move apart a little bit and then be in a liquid form instead of solid. So the difference in pressure is the biggest part. There is a difference in temperature too, but the pressure is what's causing it to be solid. All right, the outer core is our liquid layer, and we know that because of the fact that our S waves cannot travel through it. So the liquid layer of the core outside the inner core is also made of iron and nickel. Again, this is part of what causes that magnetic field. The temperature can range from 2200 in the upper part to almost 5000 near the inner core. So going from the outer part of it to the inner part, we have almost a 3,000 degree difference. And it begins at a depth of 2,900 kilometers. And again, that's going to be below the crust. If you want to include the crust, then you're looking at this range here, just based upon the fact that the crust can vary in depth. we have a 2250 kilometer radius, and that's around the inner core. So if you wanted to know the radius of what it is from the center, you would have to then add that 1300 also to figure out what that distance is. But I'm not going to worry too much about you memorizing all these distances. The moving of the outer core around the inner core. So this we know because of the movement around here, it causes a magnetic field around the Earth, which has a lot of impact on protecting us from radiation from the sun. You'll probably learn more about that if you take astronomy again.